Okay, so it's 10 o'clock. We're going to get started. As always, this is the code to do the first problem. Last class, we learned about the test set. So that's what we were doing at the end. So that brought us up to two types of error that you could consider. Let me bring over the blackboard over here. This is what we did last time. So last time we really had, we expanded our collection of errors or loss functions, aka error functions. And when we started the course, we had just one, which I called the loss of some estimator f hat. And really this should be called the true loss or something like that. True. True because it is the real thing that we really want to do. Sometimes people call this the population loss as well. So that's what statistics people call it. They think of, we have a sample of people and we're trying to do things with the sample, but what we would really like to do is talk about the whole population as a whole. And so this is the true loss or the population loss, and that is really the expected value of y minus f hat of x all squared, where you average over real values of x and y taken from the population. Like really, what would it be if we took an unseen point from the population and had an x and a y, how much error would we pick up? That was the true population loss that we had before. So we called it just a loss because it was the only one, but now we have to make sure we know it's the true loss. We also have another one that we did last time, which is called the test loss, right? And that is the loss where you hold out some points as a test set, and you said, we have these points, we didn't use them in the training, there are test points, we have some number of them, so we have some number of test points, and we just do the average of, what would it be, summing this up. So we do yi minus f hat of xi all squared. That is what we looked at before. So this was the loss for the test set. You go over the test set, you add up how good did you do on the test set. That distance squared, you add it up. Sometimes called the mean squared error, because it's the mean of the squares. And if you take the square root of it, that would be the root mean squared error, which would tell you in the units of y how far you are. There is one more that I should have talked about last time, but we ran out of time, and that is the training loss. The training loss. And that's exactly the same thing, where you add up over points, but this time you're adding up over the training set. Let me use the letter J for the training set. 1 over n training. And you do yi minus f hat. Okay, it should be j's squared. Okay. So, oh, that's a different color than the fourth one. Is this blue? Blue. Okay. No, I don't know. How did I get that funny color? Well, okay, we're on this color now. So, last class, in the first few classes, we talked about this true error, trying to minimize that. That was like the dice example, all that. We did the curves for this. In real life, you will never know this one because you don't know the distribution of x and y. So you can never actually know the true error. You can only approximate it. One way we said to approximate it is the test error. That's what we did last class. And we saw it, you get a curve that sort of reasonably matches the true thing if you could figure that out. This one I didn't talk about last class, and I should have talked about it, so we're talking about it now. This is the training loss. So same idea, but on the training set. And it's a very big confusion. Sometimes people mix up the test and the train errors, or the test and the train loss. So that's why your first mathematized question today is to please tell me the difference. One of these curves is the training loss, and one of them is the test loss. And they're both in the same problem we've been doing for like 3 classes now of the cannonball problem, doing that estimation with a characteristic width of sigma. So you average everything within sigma of u. So it's the Gaussian one where sigma is the characteristic length. So 30 degrees is like average everything within 30 degrees of u. 10 degrees, average everything within 10 degrees of u. 1 degree, average everything within 1 degree of u. And for every single value, you run the whole model, you calculate the loss. One of these curves is one of them is the training and one of them is the test. And I want you to tell me which is which. Is the red the training and blue is the test, or is it the other way around? And so you should have 2 options. Which is which? Okay. Any questions or comments about what the question is asking? Okay, I'm going to give you 1 minute to think about it. It should be, if you understand what's going on and you remember what we did last class, it should be fairly intuitive. If not, you have 1 minute to flip a coin and make your choice. Let's do 1 minute time. Okay. Okay, 12 people answered, 10 seconds left. So if you're not sure, this is your chance to take a guess. Okay, great, almost everybody has answered, fantastic. Okay, what did people think? Which one is the train and which one is the test? 13 people think blue is the test set error and red is the train set error. And 6 people think red is the test set error and blue is the train set error. The correct answer is the minority. Red is the test set error and blue is the train set error. So most people got it wrong. 68% of people got it wrong. So maybe your coin flips are very unlucky this morning. But I'm going to give you guys a minute. Just talk to the people near you. See what happened. Can you figure out, how would you figure this out now that you know the right answer? What is the right way to look at it? If you do remember, last class, this red curve was literally up there. So if you remember this U-shaped curve from last class, that would have given it away. But what is going on? Why do they have such different shapes? And what is going on there? So I'm going to give you a minute to chat with your neighbors, and then we'll come back as a group and we'll have a class discussion about what's going on. This is a really important concept to understand. Okay, so go ahead. I'll give you 2 minutes. Okay, people stop talking, so maybe you guys don't want the last 40 seconds. Does someone want to say how they thought about it? Yeah, go ahead.
Yeah, so I actually completely forgot that the delta represents the window size.
Ah, okay, okay.
I was looking for that train test curve where it goes,
okay.
goes near to 0 and
right, okay, yeah.
Seeing this, I was shocked. But then after seeing the delta, I can figure it out that initially if the number of, if the window size is small enough, then we are underfitting it. So training error will be almost 0, but then the test error will be very high. Where the two graphs are intersecting is the point where it is sweet spot. So we are actually training it very well. And after that, the graph is showing overfitting. So that I...
Okay, wait, hold on. Let me. You said lots of good things. Let me write something down. What do I want? Do I have a screen? There's a program where I can draw on the screen. What is it called? Okay, I can't find it. So we're gonna do one of these. We're gonna take a screenshot and then we're gonna copy it into here, and then we can talk about it. Okay, so great. Okay, this is the plot, and let's zoom in a bit so we can draw all over it. And okay, so I think this is a good thing that you notice. The first thing you said is that on the bottom here is sigma, which was the same kind of idea as delta. This is the idea of the window size. Okay, and that's the first thing that maybe a lot of people got wrong, is that in the textbook there was a very similar graph, but it was reversed on the x-axis. And that is because they did not have the window size on the x-axis. They had the amount of flexibility. We had a question like that, I think either last class or the class before, where we said that a very low sigma is very flexible and a very high sigma is kind of like very inflexible. So if you were reversed, then maybe you also reversed the two graphs. Okay, fantastic point. Then I think you said something about when sigma is very small, what happens?
It is underfitting.
Sigma small is underfitting. And how do you know it's underfitting?
Because we are training two small sets, so the training error is very low, but test error is very high.
So the training error is low, the train is low, and the test is high. And that means you are underfitting?
Yes.
That's underfitting. Okay, why is that underfitting?
Because we are not able to predict correctly the real life examples.
Great, so to me, not able to predict the real life examples is just the same statement as the test error is high. So test error high means not able to predict real life examples. That means your model sucks, you're doing bad.
Yeah.
I agree with that. You said it was underfitting, and you also gave me this extra piece of information that the training is low.
Number of data points.
Uh-huh.
So I think it is underfitting.
So because it's a small number of data points, therefore it's underfitting.
Yeah.
So underfitting, you're saying, is that's the same thing as small number of data points. Okay, and I think when we did this discussion in the video, the small number of data points was associated with something. Points is spelled with T, then S, points. But I don't think it was associated with underfitting. A small number of data points was associated with something else. Well, it will eventually be overfitting, not underfitting. But the small number of data points, that was the reason it had high variance.
Yeah.
High variance. Because if you only have 1 or 2 points, then you have a high variance. Just like when you average only 1 or 2 dice rolls, you could be really far off the mean just by chance. If you roll 2 6s in a row, you think the mean of the dice is a 6, even though it's 3. Like, small number of data points is high variance, and high variance went with overfitting. Overfitting. So this sigma small is not underfitting, but it is overfitting. So let's cross this out. It's overfitting. Overfitting. And another classical way you can say it's overfitting is exactly because the training thing is low. You're fitting very well to the training set. Your training set, you nailed it. You got it like right on. Good for you. Training set, you killed it. And you're going to have a picture that looks kind of like this. These black points are the training set. Look at how well my model fits the training set. Oh, I got that point, got that point, got that point up there. Wait, we went up there and got that point. We got all the training points. Super low training error. But look, we kind of overdone it with fitting the training set. We fit the training set so well that it cost us not fitting the test set. And that is the idea of overfitting. So it's not underfitting here, it's overfitting. And this is, I think, the classical name where over comes from, is you've overdone it on the training set. Your training set error is very low. And if you had a completely different training set, if you did the same procedure with a totally new training set, you got new points, then your model would completely change because of this high variance. And you would just have a whole new function that would again fit the training set very well, but would do terribly on the test set. So this side, it's not underfitting, it's overfitting. But yeah, absolutely great observation. Anyone else have any comments with that? So this is another hallmark of overfitting, right? We learned about it from the variance point of view, but you can also see overfitting from the training error. If the training error is very low and the test error is very high, then you are overfitting. That's an example of overfitting. This difference between the train and the test, so you take some point and you measure this difference. This difference. This is sometimes called the generalization error. How do we do it? Generalization. Generalization. There we go. Generalization error. That's supposed to be one long word, right? And the idea is, you've done well on the points you were given. How much worse do you do on points you haven't seen yet? That difference is called the generalization error. If you have a high generalization error, that means your model sort of like memorized the points it was given and isn't generalizing the points it hasn't seen yet. You would like that to be small. You would like that to be small. And in real life, it's always some non-zero amount. Like you will always do sort of better on the training set than the test set because you can use the training set. So you usually have a non-zero generalization error, but you would like it to be small. Yeah, it's important to not mix these up. The other thing that I see a lot of people do, this is like a really common data science error, is people, if they don't know about the test set, they just use the training set. And when it comes to minimizing the training set error, there is no U-shaped curve. When you draw these kind of plots of flexibility on the x-axis, the training set is always improving the more flexible you make your model. So you'll notice it's always getting better in this picture. This is always getting better this way. What color should I use? Let's do blue. Look, it's always improving. Improving, right? As you decrease sigma, you're doing better and better and better and better, right? Because you make the model more flexible, of course you can fit the training set better and better. So it's a really common mistake that people make, is they say like, look, as I make the sigma smaller, I'm improving. I'm getting better on the training set. Then they look just at that blue curve and they say, I'm just going to make it as small as I can. I'm just going to make it 0.01, right? And then when you do that, you end up with pictures like this that go through all the points correctly, but have a bad test error. So it's really important you don't make that mistake. And you know the difference between the train and the test, and you can keep them clear in your mind. It is good practice to never ever say the word error without specifying which one you mean, right? So we have three flavors floating around: the true error, the test error, and the training error. And it would be good practice to never say error without saying which one. Of course, in real life, people get lazy, and they will just say the error, and you have to figure out what are they talking about. But it's always a good question. Wait, which error are you talking about? Are you talking about the test error or the train error? And you should try to keep these really clear in your brain, because especially the train error is so different than the other two, right? Those two are supposed to be the same, or approximations of each other. The true error and the test error, that's what we were talking about last time. They're supposed to be approximately the same, but the training error is completely different because the f hat also depends on the points that you're measuring it on. And so it's sort of a contamination. The f hat is trained on the training points, and then you measure the error also on the training points. This one can be total garbage. In some situations, it also matches the other two, but in some situations, it's very different. Those are the ones you gotta watch out for. Okay, fantastic work. Any other questions or comments about this difference between the training error and the test error? So this is really good. This is the kind of curve you see, the kind of mistake you see people make is only doing a training thing. It's very common also in linear regression, which is what we're going to be moving towards today, to only look at the R squared value. The R squared value is some kind of training curve. And so people think, oh, a lower R squared is always better. Wait, no. Higher R squared is always better. Make the R squared as big as you can. That's the same as making the blue as small as you can, right? And this is, again, you're totally missing the actual thing you want to do is the test error, and that has a U-shaped curve sometimes where there's a sweet spot, whereas the training error does not have a sweet spot. It will always improve if you add more variables or if you make it more flexible. It will always go down. But is always going down a good thing? No, because you might be overfitting. And again, you can see this kind of picture of overfitting here. Okay, great final discussion to wrap up what we were doing last time. So we're going to start something new today with the regression. This will be the last time we do this example for a little bit. Any questions or comments about this before we do that? Yeah?
On that graph, you know the point where the test and the train, the graphs meet?
Yeah.
Does that point signify?
Yes. So that's a fantastic question. So the thing is, both of these are going to be random.
Right.
So if you pick a new test set or a new training set, it will move around, and it will move up and down. So this point where they meet doesn't actually mean anything for this graph, but you could talk about the point where they meet on average. And that would be something like the point where you have zero generalization error. This is actually, when I made this plot, I was a little surprised because almost always the test set error is always strictly higher than the training set error. So this is kind of a weird fluke situation where I don't know why it came out like this. And I was looking at the thing, and I think it was just by chance, you have a bunch of pink dots that happen to be on this curve. I think that's why the test error is so low. And you saw that last class when we did the, we plotted the true error was in blue and the test error was in red. And the test error was a lot lower than the true error. So in this graph, I think by chance, the test error has moved down a lot just by luck. If we reran it, it would not be like that. And it is more typical that the test graph is all the way above the training graph, which also makes it easier to see, but it's really important, you know that difference. Yeah. So I don't think this means anything important, but yeah, it's good to be aware of all of these issues. Anyone else for questions? Okay, so we're going to move away from this averaging thing, and the very last question we do with the averaging thing is going to be just tell me some pros or cons of the averaging thing. And the cons of this weighted average estimator are going to motivate us to move into linear regression. But I want to see what you guys think. For pros and cons, tell me one pro and one con. If you want to use more than one word, put a dot between the words because it doesn't like spaces. And you know, there's really no wrong answers here, any pros and cons that you can think of. I'm going to start a timer for, say, 2 minutes. Okay, who needs more time? Put your hand up for more time. Okay, only 3 answers, or only one person needs more time. I'll give like 30 more seconds. Okay, 10 seconds left. Put in your pros and cons. I only have 7 answers so far. So, I don't know. Okay, 8, 9. Okay, maybe we're going to have a lot of people at the last second here with a pro and a con. Okay, let's see what you said. Okay, pro, or it's simple. I like that for sure. It's easy to compute. Simplicity, simple. Yeah, non-parametric. This example is there's no parameters to consider, and so you can kind of do this no matter what data you have. Like no matter how complicated it is, you can still run it and things like that. Low bias. So by tuning the size of the neighborhood, you can control the bias and the variance, and so you can make it very low bias if you want by making a small window, Or you can make it very low variance by making a bigger window. Yeah, and you can understand the test and the train. Everything is making sense. It's very simple. There is one important thing that was not covered here that they did mention in the videos, and it has to do with what happens as soon as your problem is in a higher dimension. So if we go to this thing, this works very nicely. This is a very nice thing. Even the really overfit model, we can understand what's going on as long as it's one-dimensional. So the x's are one-dimensional and the y's are one-dimensional. This is actually a really fantastic algorithm whenever you have one-dimensional data. Maybe people mentioned this under cons. Let me check the cons first before I start talking too much. Yeah, high dimensions. Okay, at least one person mentioned it. So not suitable under high variance. Maybe they meant high dimensions, but high dimensions, cursive dimensionality. So this is great. And this is the big thing. Even though it's very simple and it works nicely, when you're in high dimensions, this thing stops being as nice and simple because you can't just average in the x1 direction. You have to average in multiple directions. So this is a really great model for one-dimensional things. In fact, the most common place I have seen this algorithm used in real life is when you're tracking your weight over time. You step on the scale. This is how they smooth it out, right? Like one day I ate a big burger and then I weighed a little bit more. But then if we smooth it out a little bit, we go to one of these ones. See, like I ate a big burger, but I didn't really go the full way. So it's really useful for one-dimensional data. It's also useful, there's something called kernel density estimation. Let me get the Wikipedia page, which is very similar. Where instead of using a histogram, you can make a smoothed out version of a histogram. So instead of a histogram like this, you can make a smoothed out version using the exact same algorithm we did. Again, this works really nicely because it's one-dimensional. So for one-dimensional stuff, this is a fantastic algorithm. But in high dimensions, it starts to get bad because the points are very far apart. When you're in 100 dimensions, the nearest point might be really far away. So it's not like you have a notion of these two are really close. They'll be close in some dimensions and far away in other dimensions, and then it's hard to make sense of what's going on. So this is the major con that people said. Even in those high dimensions, I think it's still pretty computationally fast because you just have to do nearby neighbors. So it kind of is a function of the number of data points, which all things are. But high dimensions is the main thing. High variance, again, you can control the variance and the bias by just tuning the size of the window. So that's way, but this is the big downside is in high dimensions, it is not as good. There is one other really big downside, which I think nobody mentioned, which is that it is hard to interpret what's going on. So suppose we wanted to know, does x actually affect y? Like we're trying to figure out, does the x have any effect on y, and we have this data. And then we come out with this red graph, and we're like, look, sometimes it goes up, sometimes it goes down. So does x have a positive effect on y, or a negative effect, or what? And it's very hard, given that red graph, to say what it is. So, like, yeah, if x is the amount of vegetables I eat, and y is like my score on the exam, should I eat more vegetables, or should I stop eating vegetables? Like, it's not, I don't know from that red graph. It's unclear to me. Of course, the answer is, if you did it properly, it would look like this, and you have to eat just the right amount of vegetables to do well on the exam. But it's quite difficult to interpret what is the overall trend. So it's very good for drawing a line and like maybe good for estimates, but it's bad for interpreting. And this is the graph they had in the textbook and the videos. They had this interpretability graph, which isn't loading. Oh, wait, there it is. Okay. And they had flexibility versus interpretability. So some things are very flexible and can do all sorts of things. Things like deep learning, bagging and boosting, some complicated methods. But the model that we just did is also like that. It can be very flexible. By changing the distance function, you can do all sorts of things with it. But the interpretability is very low. So these models, they give you a function, an f hat function, but nothing else. And that f hat function, it's quite difficult to use the f hat function to figure out what is it really saying. Is eating more vegetables good or bad? On the other side, you have things that are less flexible, but are very interpretable. And what we're going to do is we're going to start with linear regression, also known as least squares, which is fitting these linear things. And it's very simple, and it's very interpretable, because you can look at the coefficients, and you can see, are the coefficients positive or negative? What is the association here? And not only can you say whether or not they're positive or negative, there's also a theory that tells you how much they vary. And so that's where we're going to start, is understanding in what ways can you interpret things? And in what ways does this linear regression, it's so simple that you can have this extra layer of interpretability that you give up as soon as you move to more complicated models. So we're going to start with some of that. We're going to start talking about the standard errors for a little bit. But any sort of overall questions about moving to linear regression or anything they said in those videos that you're supposed to be watching before class? Okay, so let's start with an example. Just like we did before, I'm going to start with a very simple kind of like dice rolly example. And we're going to move from the dice rolly example into real examples. It's going to get harder and harder. But to start with the absolutely core mathematical principle for standard errors, here is the most simple demonstration of what is going on with these standard errors in this 95% confidence interval business. So imagine simulating 100 independent, mean 0, variance 1, Gaussian random variables. So this is kind of like rolling 100 dice, right? But instead of dice that have 4 sides, they're dice that can be any number between negative infinity and positive infinity. It's just that they happen to have a bell curve shape between negative 1 and 1. You know, they're very likely to be near 0, and their typical scale away from 0 is 1. Let A be the average of these. So add them all up, divide by 100. That's the average A. A itself is a random variable. So we have x1, x2 are all random variables. A is a random variable. I'm asking you, what is the mean of A? What is A equal to on average? And please tell me a 95% confidence interval for A. So please give me an interval where you think there's a 95% chance that A will live in that interval. And if you did some of those calculations, or you remember from your statistics class, this is starting to be more statistics and less probability, then you should be able to figure these things out. So the mean, this is something we did. There's a calculation we did earlier in class that also is related to this. You do have to remember a secret number from stats class about the bell curve, but you can also look that up. I'll give you guys like 2 or 3 minutes to work on this. Feel free to chat with your neighbors if you're like, I don't remember, what is the secret number? Then you can ask your neighbor. Okay, so I'll give you 2 or 3 minutes and then we'll take it up. Okay, there's like 20 seconds left. Who needs more time?
Variance
Lots of people for more time. Let me give you another minute.
three intervals.
Okay, who still needs more time? I'm happy to give more time if you guys are being productive. Okay, let me give a few more minutes. Yeah. Okay, I really am gonna stop this time. So put in your guess, even if you just know the mean, and put in an I don't know for the 5, 4, 3, 2, 1 for the confidence interval. That's okay. Or maybe you did some like partial calculation. You calculated something and it wasn't the confidence interval. Just put that something in here, and then I will respond appropriately. All right. Okay, so let's start with the mean, and let's see what you guys put. The mean, 15 people said 0, which is the right answer. If you put in 50.5, you were getting confused with a 100-sided dice. Right? A 100-sided dice has a mean of 50.5, but there's not a 100-sided dice. There's 100 different things. So it's like we're rolling 100 different dices. There is no 100-sided dice. So 0 is the correct answer. Why is 0 the correct answer? Let's take a quick calculation here. So now we're on to this problem about Gaussians. And so we're doing A, which is, start again, A is the sum, 1 over 100, and it's the sum from I equals 1 to 100 of xi. If you want to do the average, the expected value, you can take the expected value of both sides. And the nice thing about expected value is it plays nicely with sums. So the expected value of the sum, what is the average of A plus B? It's the same thing as the expected value of A plus the expected value of B. You can change the order. Even multiplying by 1 over 100 is also fine. So you can change it like this. So the mean of A is the sum of the means of the xi. But we said they're mean 0. So this is adding up 0 100 times. So if you want this as 1 over 100 times 100 times 0. 100 copies of 0 still gives 0 in the end. And that is why it's mean 0. So very good, people did that. The next thing we had to do is calculate the confidence interval. The confidence interval. I want to see what people said. So let's do the right end of the confidence interval and see what people said. So some people, this is the right answer, is this 0.196, which if you put into just some number of decimal places, it would still count it as correct. Okay, is it going to show me? Reveal correct answer. Okay. But I want to see, did people put in some other things? Yeah, 1.96. Okay, that's related to something. Okay, so some people had, 6 people I think got it right, and some people, 1.96 is somehow related. But the thing you got to do before you do the confidence interval is there's an actual middle step that you sort of are forced to do, and that is to compute the variance. The variance of A. How many people thought, let's try to compute the variance and try to do the variance? Put your hand up if you are thinking about variance. 1 person, 2 people, a few people. Not many. Okay, so this is very good. The confidence interval is a range, and the variance is telling you approximately the size of the range. So if you know the variance, then you can use that to kind of get these confidence intervals. So the way I would 100% do this problem is I would just go with the variance to begin with and work on that. So what is the variance? And remember, the variance is the same as this thing that we've done before many times. The A minus the expected value of A all squared. In this case, the expected value of A is 0. So this thing is the expected value of A squared. So how big is this thing when you square it, an average? That's like the mean squared size of A. That's the variance here, because there is no expected value. So normally the variance is the mean squared difference from the mean. But because the mean is 0, it's just the mean squared size. Just how big is it on average. So it's the expected value of this thing squared. So we got to do the expected value of 1 over 100 times the sum, I equals 1 to 100, of xi all squared. Okay, 1 over 100 on the front, squared, that's easy, that pulls out. That's a 1 over 100 squared. And then we do the expected value of the sum from I equals 1 to 100 of xi all squared. And this is one, now you should be saying, we did this one in class a while ago, right? If you have a bunch of random variables squared and you do their expected value, the Pythagoras theorem for random variables, as long as they're uncorrelated, which they are here because we said they were independent, they have nothing to do with each other. This is Pythagoras for the 4th time in the course. 1 over 100 squared, and then you can pull out the sum and just do the expected value of each thing squared, xi squared. Okay. And the expected value of xi squared, that is the variance, because each of the things were mean 0. So this is the sum from I equals 1 to 100 of the variance of xi. Okay, and this thing that we've proven, the variance of A is the sum of the variances of the terms. This always works. When you add up independent or uncorrelated things, the variance of the sum is the sum of the variances. That always works. And in this case, we multiplied by 1 over 100 to get the average, right? A was not the sum of the x's, it was the sum of the x's divided by 100. That pulls out with a 1 over 100 squared, because variances are squarey. Okay, so variances are squarey. We have to do this thing. We're summing up the variance, but the variance of each one was 1. We were told they were mean 0, variance 1. So this is 100 squared. There's 100 of them, and each one is 1. So that's the final answer. 1 over 100 squared times 100 copies. Each guy gave a 1. And if you do some simplifying, this is 1 over 100, which is something we saw before. When you roll n dice, you get 1 over n as the variance. You average n Gaussians, you get 1 over n as the variance. Any questions or comments about that calculation for the variance? Feel free to stop me if it's too fast or if there's a step that I should explain. This is a chance for you to ask. Okay, so the variance is 1 over 100. What does that have to do with the confidence interval? That was the actual question. Well, if you know the variance, you can figure out the standard deviation. The standard deviation of A, which is the square root of the variance, right? The variance is like the mean squared size, and the standard deviation is like the root mean squared size. It's how big is it typically by taking the square root of the thing that was squared. And in this case, it's the square root of 1 over 100. It's 1 over 10, also known as 0.1. And what this says is the length scale of this thing is going to be 0.1. We should expect when we run it that it'll be like 0.1, 0.2. It would be very unlikely to see something like 7, right? 7 would be 70 standard deviations. We expect some order 1, like some small number of standard deviation. So this is telling us the length scale of the random variable. What is the confidence interval? And this was the secret number that you have to remember from your stats class, is that 1.96 standard deviations is what goes with a 95% confidence interval. So this was the secret information. Sometimes people will just remember this as 2, which is also fine. 2 standard deviations. So in general, if you go from minus 2 SD to plus 2 SD, you have a 95% chance of being somewhere in the range of minus 2 to plus 2 standard deviations. The standard deviation is like the length scale. And this magical formula, 1.96, tells you how many length scales will capture 95%. And this works for anything that is approximately Gaussian. When you're averaging things, it becomes Gaussian. Let me tell you a funny story. So I made a video about Gaussian random variables. And people in the comments said, you're saying Gaussian wrong. It should be 3 syllables. It should be Gaussian. All right? And to me, Gaussian sounds very British. And then, this is the exciting part, I emailed a guy who does pronunciations of things. And I was like, I say it like this. Why is everybody giving me a hard time? And he was like, oh, this is like a common thing. Like young people in the US and Canada, they take 3-syllable words and they smoosh them down into 2 syllables. And there's a whole bunch of words that are like this. So if you want to be proper, don't say Gaussian like me. Gaussian is like street probability. Say Gaussian. That's the right way to say it. But I'm going to say Gaussian because, I'm the professor. So that's how it goes. Okay. So 2 standard deviations, and this works for Gaussian random variables. And it really is a calculation of if you have a bell curve and you calculate the area in between negative 2 standard deviations and positive 2 standard deviations. This area is a 95% area of the bell curve. This percent didn't turn out too good. So it really is something about Gaussians, and when you add up a lot of variables, it's approximately Gaussian. So it's a good approximation anytime you're adding up a lot of things. So congratulations to the people who got it right. You had a really good, solid statistics class. If you put in 1.96, you remembered the secret number, but you did not remember that it's the number of standard deviations, not just always 1.96. And let me see, were there any other comments? Some people maybe forgot the 1 or something, or divided it by 2. I'm not sure. This one should always be the negative of the other one. Oh, interesting. Oh yeah, okay, so this one. Oh, I typed this one wrong. Okay, this was look, I have the wrong answer in here. This is the right answer. So 16% of people got this one right. I typed it in wrong. It should be 0.196 to negative 0.196 is the correct final answer. So in our case, final answer. So I typed it in wrong in Mathematize. Very, very good. So minus 0.196 to positive 0.196. Or negative 0.2 to positive 0.2 is the nice rounded version. Okay, and that's a 95% confidence interval because the standard deviation was 0.1. And that's how it works. Okay, so some people remembered, some people remembered partially, some people did not remember, which is okay, because the whole point of the course is to learn. Okay, any questions or comments about the calculation? That was all pen and paper math. And in a second, we're going to do computer math. Okay, so let's see, what does this really mean? And I made a notebook to show us what this means in practice. The notebook went away. Okay, the notebook, I want to put it here. Can I add this thing? Okay. Okay, so here's the question. We have 100 Gaussians, or Gaussians if you're British, n equals 100, and the standard error is always 1 over the square root of the number. So in our case, it was 100. That's why we got 1/10. And a 95% confidence interval, you can do -2 to 2. And so this is what it calculates. This is doing the pen and paper math that we just did. 100, -0.2 to positive 0.2. Or if you want to be more precise, you could do -0.196 and have an extra decimal place. And then this is the fun part that you can do on the computer that you can't do on paper, is I ran it 20 times. So I ran it 20 times. I rolled 100 Gaussians once. I did it again. I did it again. I did it again. For a loop, just run it 20 times. Okay? And A, we just said it's the mean of running n random variables. And then please tell me the average. So tell me what was A. And then tell me, is it within the confidence interval that you said? Yes or no? And so we calculated the standard deviation as 0.1. So we're expecting numbers that are on the order of 0.1. So here is the first test. The average was -0.03. That's on the scale of 0.1. That makes perfect sense, right? It's not like 100 times smaller than 0.1. It's not 100 times bigger than 0.1. It's on the order of 0.1. And is it in the 95% confidence interval? Yes, it is. True. Then I ran it again. It was positive 0.02. Is it in there? Yes. 0.09, 0.14. True, 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 until you get to -0.2. And that is, according to this, is just outside the confidence interval, right? So it was just barely outside. False. And then I ran it some more times, right? Because we did it 20 times. So here they are. Here they are, the 20 times. And you'll see there's one other one where it was -0.22. And this looks about right. So in our 20 trials, it was outside the confidence interval twice. On average, we expect it to be outside one time, right? 95% confidence interval means you run it 20 times. One of them should typically be outside the range. The other 19 should be inside the range. We can run it again and see what happens. So let's run it one more time. Do I have to? I probably have to run this first, or it'll yell at me. Okay. Import the packages, then run it again. Okay, how many did we get this time? True, 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 true. One false there. A second false there. That's 2. Okay, we got 2 again. Let's do it one more time. True, 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 true. One false there. And the rest are true. So this one's perfect. Look, we got exactly one false. So I think we did the calculation correctly. The 95% confidence interval captures 95% of the things. And I think the other important insight is that the standard deviation is the typical size. This is the kind of thing, the kind of intuition that you should have. And it's always centered around 0, like the average of these is 0. Okay. So again, if you understand this, you're understanding. You can really double check if you're good at programming. Let's not run it 20 times. Let's run it 1,000,000 times. Okay, look, I ran the experiment 1,000,000 times. And if you run it 1,000,000 times, you better put in the accurate decimals or you're going to start to have error. And here I did it with the array broadcasting we talked about last time. So here is some axis equals -1. There's something going on with making multiple axes. And even though there's 1,000,000 samples, I can run it in 5 seconds on my computer. So 1,000,000 samples of 100 each. I ran 100 million dice rolls in this simulation. It ran in 5 seconds. And you can still see the percentage outside, instead of counting them one by one, I have the computer count for me, was 5.02%. So it really does work. This confidence interval stuff really does capture what's going on. For other things, it'll be more of an approximation, but this is the right kind of thing you want. Using statistics or probability, we can capture the idea of how big things are typically and understand how much they vary typically. Okay, so that's this example. Any questions or comments about this? Anything unclear? This is a good exercise if you want to get good at this array broadcasting and thinking in terms of vectors and axes. This is a really simple example where you should try to read it and understand what's going on. So when I do this thing, what is A? What does it do? What is the shape of A? What does it do when I do this? I do np.absolute value of A greater than this. What is that? What is this step doing? Things like that. So a really good one to check out because you can write really fast code. Otherwise, if you do it with a for loop, it will not finish in time. Okay. Okay, so why are we doing all this? What does this have to do with anything? Well, in the textbook, we started with a simple regression with a one-dimensional regression, and it looks something like this. So we had some points. We had 10 points of data, and just like we were doing before, we have a secret function in blue, which is the secret relationship between the x and the y that you don't know and you would like to estimate by using linear regression. So there's the 10 points, and here is the secret blue function that we don't know, and that is the computer setting everything up to run this. And now we're going to run this linear regression stuff, which you can think of as just estimating what is the slope and the intercept of that line in blue. And if you do it, you get something that looks like this. So here we go. So the red line is the estimated. The true one, which is secret, had a beta 0 of 2.0. Beta 0 is the intercept. And it had a beta 1 of 3, which means the slope is 3. So it's the equation 3x plus 2 is the blue line. And what did we get when we ran the regression? We did beta hat 0, the estimated intercept was 2.08, and beta hat 1 was 2.94. So pretty close to the actual thing. That red line is very close to the blue line. And if it was like the thing we did before, that's all we could do. We could just have the red line, and we say like, okay, we have the red line. You know, in real life, we don't know the blue line. We just like cross our fingers and hope that they're close. Maybe we use a test set to see how close they are. But with linear regression, because it's so simple, we have the same kind of standard error thing that we had for the Gaussian and invariables, which is that we can measure how close these two things are typically with a confidence interval. And the way you should think of what is going on here is, so you can calculate the confidence intervals, and you can think of what would happen if you reran the experiment a bunch of times. So here I've reran the experiment, I think 20 times, just like we redid the experiment 20 times for the Gaussian dice rolls, and you get 20 different lines, right? So that red line was one of these possible samples. And the standard error should tell you how much variability is there in the slope and the intercept. So you get 20 different things when you run the experiment 20 times. And by doing this calculation, you can figure out what is the typical distance between the curves. Like, how far apart are they? And to do that, you can plot them in the space of beta 0 versus beta 1, right? So one of these lines, when we did it in red, beta 0 was 2.08, and beta 1 was 2.94. And so that would be the point at 2.0, 2.08, 2.94. 2.08 is like right around here, and then 2.94 is somewhere here. That would be a point like here. So the red point that we did would be some point over here. And every time you run it, you get a different beta 0 and a different beta 1. So all of these dots represent a line represented as the slope and the intercept. So it's the same picture as this, but represented in a different way. These are the lines. These are the slope and the intercept of the lines. And the nice thing, and this is just very similar to the Gaussians we just did, exact same idea, you can calculate the 95% confidence interval for beta 0 and beta 1. For the Gaussian, it was one number, so it was one interval. For beta 0, it's one interval. It's going from 1.4 to 2.6. And for beta 1, it's going between 2.5 and 3.5. And so altogether, you can think of that as a rectangle. And we're saying that when we run this thing, 95% of the time, the estimated light blue dot will be within the rectangle of the dark blue dot. So we have a sense of how close things are. And we can calculate that theoretically. And that's what's so nice about it. So the green box is just from theory. You don't need to redo the experiment many times. You can just calculate the size of the green box. And you think that most of the time, the true thing you want and what you're looking for are within the green box. Of course, it's not every time, right? Occasionally it goes wrong. Here are 3 points that went wrong. They are within the bounds of beta 0, but they are outside of the bounds of beta 1. And there's typically, for every 20 points you draw, one of them will be outside. But okay, there's beta 0 and beta 1. So if you do 20 points, maybe you expect 2 excursions. We got 3 here. We could redo it. Let's redo the whole thing. And it should be, again, typically 1. So just like we reran it to do this guy, you can rerun it again. So let me just do a run all. Runtime. Let's run all. And it'll just redo everything. Okay. Average a million things. Do one of these. Give me some numbers. And then redo everything. Did I output the exact same ones? Oh, there's probably some random seed somewhere. Where's the random seed? Random seed 1. Okay, let's put in random seed 9 and start over. That'll really give me a different one. Okay. Is it running? Oh, the one that takes a long time is the million samples. Okay. So here it came out to 2.01 and 3.00 for the red And then when we redid it, we get some different thing. And I don't know, why didn't it draw the square? There's some kind of bug. Okay, that's exciting. That's the fun part about coding live. Why don't you like me? Oh, there was an error. Oh, it tried to divide by 0. Okay, there's some kind of, you know what I think happened? We estimated it so perfectly that it tried to divide by 0 in doing it. Let's redo the whole thing. I'm gonna pick a different number. Let's pick 90. And then let's run these again. And this time, maybe it won't crash. Okay, there we go. So this time I ran it. Okay, there was some kind of bug. And over here, if we look at this guy, now exactly one of them, no wait, 2 of them are outside, right? One is outside here, one is outside there. But most of them are within this confidence interval. And you can calculate the confidence interval just using theory. So this is the really nice thing about linear regression that people like, is you have this theory that tells you how far should things be. Okay, this is the first lesson on linear regression. We have 3 worksheets like this in the folder on the GitHub. But this is the first one that has only X's and Y's. This is like the simplest possible one. Are there any questions or comments about this linear regression thing? And this picture of looking in the space of parameters. And the extra tool you get that we didn't have before is this confidence interval stuff. Okay. So one really common thing you can do is once you have the confidence interval, you have the measurement, you can say, okay, I think beta hat 0 is 2, and I have this confidence interval, and then you can use that to say, is it significant or not, right? Before, we just had some funny curve. I didn't know what significant meant. But now we can combine our estimate and the uncertainty, and we can say, is it significant? Okay, but the question is, what does significant mean? So when people say it's significant, which of these 3 sentences is the most accurate answer to what they mean? And pick your favorite. So I'll give you 1 minute to think about that. Okay, people put it in right away, so maybe you guys all know what significant means. Oh boy. 3-way split. We got an 876. So of 21 people who voted, the most has 8 and the least has 6. So of course this means we must go discuss, try to come to a consensus. I'll open it up again, talk to your neighbors, see if you can convince each other what does significant mean, and then we will re-vote. And then if there's still no consensus, then we'll have a discussion. But yeah, talk to your neighbors and we're going to re-vote. Okay, I opened it up again, so you have to re-vote. Even if you didn't change your answer, you must re-vote. But I'll give you 2 minutes to have a good discussion with the people near you and think, well, I don't know, is there some way, some thought experiment you can come up with to figure out which one of these it is? So feel free to keep talking.
तेरे को जो दिखाई दे रहा है
Okay, people stop talking. Let me stop the timer then. There's 18 votes. Maybe one or two people still haven't put in their vote. Well, let's see what you guys think. Did the votes change, and in what way? Okay. So now we're 965, so still pretty split, but I guess this middle one is a little bit more popular. Does anybody want to advocate for any of these three options? The thing is, all three of them have something to do with significant, right? So it's like none of them are completely wrong, but one of them is definitely the best. So maybe someone wants to volunteer why they picked an answer and what they think it has to do with significance? Yeah.
So
Which one did you say, first of all?
that is the popular one.
The popular one. The effect is unlikely to be due to chance. Okay,
Yeah,
tell me about that one.
the reason is that both the answers 6 and the 5 one, they are
Yeah.
related to it, but yeah, like you said, why I think this is right is because as a data scientist we are generally using for more complex models linear regression, a way to figure out which attributes really have an impact in real life. So sometimes even in the initial phases of classes, I remember you talked about that there is some kind of correlation happening between some random variables, let's say some comedy types of correlations. I can just get an
Okay.
example. So in there, the correlation may be high, other stats like BIC and some things can be there. But if it is not significant, then we should not see it in the linear regression.
Okay, yeah, this is great. So I think the one sentence that stood out to me is you said we want to figure out what matters and what doesn't matter,
Yes.
right? And if you're trying to figure out what matters and what doesn't matter, like the thing you said in the middle, which is if it's unlikely to be due to chance, then we can say that matters, right? Because like if it's unlikely to be due to chance, that means there's probably something there and maybe it matters. But wouldn't the effect being large also be something that matters? Because if the effect is large, isn't that also saying it matters?
Yeah,
So-
it matters, but even small effects can matter. So it is not like
Okay.
it has always to be large. And yes, if
Okay.
the effect is significant, then its certainty
Okay.
maybe will be low.
So you're saying if it's unlikely to be due to chance, then it's definitely large. No, wait, the other way around. If it's large, then it's definitely unlikely to be due to chance.
Because there can always be outliers in our data set.
Say that one more time.
We can always have outliers in our data set
Uh-huh.
that can lie on the extreme edges of
Right.
the curve.
Yes.
And to avoid that, because
Yeah.
we know that outliers will be there, we have to be confident that most of it is going to be.
Yeah, great. Okay, this is good. So this is it. We're thinking about outliers. So outliers are data points that are like far from the typical. Like if we go to say this picture, here's some data, right? And in this one there were really no outliers. But if there was a point that was like way over here, that point would be an outlier. And you're saying like we shouldn't worry too much about those. Yeah, this is great. So I think the idea of all the data points are getting distilled down into, in this mathematized question, it's what is called the effect, right? So the outliers will be somehow incorporated into how big was the effect or something like that. And mathematically, that is going into these coefficients, beta hat 0 and beta hat 1. So if you have points that are outliers, that will pull beta hat 0 and beta hat 1 in a certain way. And then you can measure how big is the effect by looking at beta hat 0 and beta hat 1. So the individual points being outliers, we're talking about is the effect an outlier. So is beta hat 1 and beta hat 0, are they accurately representing the true thing? And of course it's related to the points that are outliers because the points that are outliers will pull on beta hat 0 and beta hat 1, right? So if we look at in beta space is this plot where we have on the x-axis beta 0 and on the y-axis beta 1. And these are not data points, right? These are 10 data points distilled down into one number, actually two numbers, which tell us, quote, the effect, right? And if you have outliers in the data, it will pull these points around. So maybe you have a point that's way below where it's supposed to be, and that will make beta 1 a lot smaller than it's supposed to be. Like it's pulling the slope down. But these points will move around, and that is what we want to look at. So when we say the effect, somehow we're taking our model and we're distilling the effect of all the data points into one idea, the effect size, and in linear regression, the effect size really can be thought of as the actual coefficients themselves. Okay, so this is good. This is a great discussion. Anybody else have anything to add? I haven't revealed the right answer yet. So anybody want to say about the other options? So somebody spoke up for the slightly more popular one that 9 people picked. Does anyone want to speak up for the other 2? So let me clarify a little bit. These are good. This is a really good question because in real life you spend a lot of time speaking to other people with words. So words matter. Like words are an important thing. That's how real life operates. But let's translate these words into what they are mathematically, and then we'll have a kind of a more mathematically, a more precise version of what's going on. So I'm going to take this picture. Let's do another copy paste of this picture. So this is beta 0 and beta 1, and let me copy paste this into our Blackboard, and then let me mark on and try to explain what these 3 ideas would be mathematically. So let's take the first one. The effect is large. That was one. Is large. That's one thing. The other one was the effect has low uncertainty. Has low uncertainty. And the last one was it was unlikely to be due to chance. Unlikely to be due to chance. And all 3 of these, you can translate them directly into mathematical statements about the size or the relative something about beta 1 and beta 0. Let's focus on only beta 1. So in some situations, you might be worried about beta 0. That's the intercept. That's saying if x was 0, what is the effect of nothing, right? And then you would care about that. But very often you care about beta 1. And beta 1 is telling you what is the effect that x has on y, right? If beta 1 is very large, that means a small change in x causes a big change in y. And if beta 1 is very close to 0, that means okay, you change x a lot and it barely doesn't change y very much at all. So the effect is large, I think is literally just translates into is this one. Let's separate these like this. The effect is large, I think is just is beta 1 large, right? That is how I would translate it into math. As a number, I guess maybe the absolute value of beta 1. Okay? Because if it's very positive or very negative, it has a big effect. So is beta 1 large? Okay? Is it a big number? If it's a small number that's close to 0, that's a small effect. If it's a big number, that's a big effect. That's how I would translate is beta 1 large, the effect is large. On the other hand, the effect has low uncertainty. I think that's not a statement about beta 1 at all, but it's about the size of this 95% confidence interval. So is the size of the window large? That's, I guess it's low uncertainty, so is the size of the window small? That's how I would translate this. And it's looking at the size of this window. So the effect size is what is the actual point? Let's pick one point and pretend we're at this point. Let's pretend we're at this point. So again, these dots represent all different samples. But in real life, you only have one sample. Let's pretend this is our sample. So one of them is the size of beta 1, which in this case is 3. And the other one is the size of the window. Okay? And again, it's up to your interpretation. Is 3 a small number or a large number? Well, it depends on what you're looking at. But you can have a sense of is it large or small, right? So you can say, in some situations, you would say 3, that's a very big effect, right? You don't want to have 3 times as many heart attacks. In another situation, you say, well, it's only $3 extra, and that's small. But the point is, the effect size is the size of beta, and the uncertainty is really also something that makes sense. It's the size of the interval containing beta 1. Okay, what about this unlikely to be due to chance? How would you translate that into something about beta 1 and the rectangle containing beta 1? Does anyone have an idea of how you would translate that? So again, there's a nice one-sentence way to make it precise, and it involves both the rectangle and the absolute position of beta 1. Yeah?
Does
the point lie inside confidence interval?
Does which point lie inside the confidence interval? That is the right answer if you tell me the right point. Which point are we talking about? Does which point lie inside the confidence interval? So right now the confidence interval
True beta lies in
is 3.6 to 2.4. And you are right, we are searching for a particular point inside that interval.
Beta.
Which one?
Beta.
The real value.
Yes, true value.
So the true value is this. This is a great point. The true value. Yes. So in real life, right, we have one data set, we get the purple point, we get the confidence interval around the purple point, we say we think it's between 2.4 and 3.6, and the true value we got was, I don't know, let's say it's 3.0, because that makes things nice and symmetric. And in real life, we don't know the true value, right? In real life, you will never know the true value. If you did know the true value, you could say, are we accurate? Did we get it right? Was it, like if it was real life, you could go to this thing, and you can say, are we inside or outside? You have this true or false. But in real life, you will never know that. So if you know the true thing, you can say, did we estimate it correctly or not? Did we do a good job or not? But in real life, you will never ever know that. You will just know, my measurement says the 95% confidence interval is 2.4 to 3.6. So if everything is going correctly, 95% of the time when I run it, if I reran a different universe and did it again, 95% of the time I would have it in there somewhere. But you will never know, are you in the universe, the 5% unlucky universe where it's outside? So you will never ever know, in real life, if the true value is inside. So unlikely to be due to chance is not something about the true value. It's something only about the interval that you can measure from your measurement. But yeah, you have exactly the right idea. It's about whether or not this contains a specific point. Does anyone else want to take a guess what it could be? Yeah, go ahead.
The outlier again?
The outlier. Again, are you talking about an outlier for the estimates, like these blue dots, or the outliers of the original points?
I don't understand.
Well, so the blue dots, each blue dot is actually 10 data points that are condensed into one thing, right? So I think maybe for the purposes of this discussion, let's delete all of these ones. Let's delete all of these ones. The only things that matter are that purple one and the true value, right? So the true value is the real value of beta 0, beta 1. And for 10 particular points, you have one data set of 10 points. We got this purple one. Because it was a computer simulation, I ran it 20 times to show you how the confidence interval works. But in real life, you only get one dot. You get just that one purple dot. And you get the confidence interval, and you get the green rectangle around the purple dot. But that's all you get. So what do you mean by an outlier? Anyone else have ideas? The observed beta. Yeah, so the observed beta is the purple dot, right? So there's something about the purple dot. Here's a question. So let's pretend these x's and y's are something. Let's do x is the number of vegetables I eat, and y is the amount, the grade I get on the exam. Okay? We want to know, does eating more vegetables help me on the exam or not? Right? Because I want to know, should I eat vegetables or should I stop eating vegetables? Okay? So what do I actually care about? 3 is good. If it was 3, that would be great. That would mean if I eat the vegetables, I get 3 points higher. But I just want to answer the question, should I eat more or not eat more? What do I need to know about this? If the question is, should I eat more or not eat more? I don't actually care if it's 3, right? It could be 1. So is the effect being large? I don't actually care if it's large or not, right? I want to know if what?
If there is a positive correlation between...
If it's positive, I want to know if it's positive. That's what I want to know. So if I want to know if it's positive, I want to be sure that this thing is positive. I don't actually care if it's large. I don't actually care if the window size is small. What if right, in this example, it was 2.4 to 3.6. Let's do another example. Let's pretend it worked out that the actual estimate was 1.1, but let's pretend that the interval worked out to be negative 0.9 to positive 2 point something. So in some other example, the actual estimate works out to 1.1, but the confidence interval goes from negative 0.9 to plus 2.1. So the rectangle is centered at 1.1. The green rectangle is like this, but it includes all the way down to negative 0.9. In that case, it is positive, but because of the uncertainty, I can't be sure if it's really positive, right? I could have equally well came up with points that are down here that are like negative 0.3. That is inside the rectangle. That happens 95% of the time. So unlikely to be due to chance, I would say, translates into, does the confidence interval contain 0 or not? Does the confidence interval contain 0 or not? That is really what we want. And you can see it's a combination of the effect being large and the size of the window. If the effect is bigger than the size of the uncertainty window, then it won't contain 0. And if the size of the uncertainty is bigger than the size of the effect, then it will contain 0. So it is the mixture of these two things that make it unlikely to be due to chance. And that is the kind of thing when we say, okay, we're pretty sure eating vegetables will help your exam score because there's a 95% chance that it's somewhere in this positive region. We're 95% sure that beta should at least be positive. And that is what people mean when they say significant. So that is the correct answer. And I think people did shift slightly into that one, so some people had some good discussion. Next class, we're going to do more of this stuff with multiple effects. So far it's all been 1x, 1y. Next class, it's going to start being 2 x's and a y, and it gets even more complicated. So make sure you go watch the video about the multiple linear regression, which was technically for today. I moved it for today thinking we would get to that today, but we did not. So make sure you watch that video if you haven't already, and I'll see you guys on Tuesday. And don't forget the colloquium is on Tuesday, so right after class, you should put in your calendar to go to the colloquium. Okay, see you guys. I'm a little over time. Thanks for waiting, and see you next class.